Hello and welcome to this new episode which begins a new chapter. And in this video, we are going to look at what machine learning really is. So in previous videos, I kept mentioning that AI has to do with giving new abilities to computers, helping computers to take intelligent decisions, or helping to let computers mimic the cognitive abilities of humans, okay? But now we are going to look at a formal definition of machine learning. And these formal definitions we are going to look at are definitions that were written by two pioneers of the field, Arthur Samuel and then Tom Mitchell. So, Arthur Samuel defines machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. So in the previous video, I showed you the paradigm shift between traditional software engineering approach and the machine learning approach. And in that video, we learned that in traditional software engineering approach, you need to know the rules, you translate those rules into a program, you feed in input, and then the rules is used to come up with an output. But once you get into the machine learning approach, things are reversed a bit in the sense that you feed in data, that is your input, and then expected output, and your model by training is able to figure out the rules that are supposed to be used to translate the input into the given output. So what Arthur Samuel is saying is that machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. So the term here is without being explicitly programmed. And that is what we saw in the previous video, that the model is able to figure out the rules on its own as opposed to traditional software engineering where the programmer has to translate rules into program instructions that are supposed to be followed. Now, Arthur Samuel's definition is good, but it's kind of vague. It leaves rooms for a lot of questions. Okay, so Tom Mitchell also came up with another good definition of machine learning, and this is what Tom Mitchell describes as a well-posed learning problem. He says a computer program is set to learn from experience E. Okay, it's set to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. So the three things that we need to look out for in this definition is the fact that whenever we are doing machine learning, we need to have a task T, which is the problem that we want to solve, okay, and then we need to have a performance measure. How are we going to measure how well our computer is doing, our software is doing, or our AI model is doing? And then E here is the experience. Okay, so if you look at Tom Mitchell's definition, I'm going to go over it again. He says, a well-posed learning problem. A computer program is set to learn from experience E with respect to some task T and some performance measure P if its performance on task T as measured by P improves with experience E. In everyday life, when we say you have learned, what we actually mean is that by virtue of experiencing or doing something over and over and over, you would have acquired some intuition, or you would have learned certain things based on the repetition, the fact that you have been doing the thing over and over and over. So once we say someone is an experienced engineer or someone is an experienced driver, what we mean is that by virtue of driving for several years, doing that every day, the person have learned some intuition and some skills that the new driver wouldn't have. And so experience is not something that can be shared easily, that can be passed on. It is built by virtue of repeatedly doing the same things over and over and over. So Tom Mitchell is saying that once you claim to do machine learning, or you claim to let a computer software learn on its own, you need to be sure that you have a task that you want the machine learning model to solve. So example of a task can be building a spam filter, or digit recognizer, or any problem that you feel you want to use machine learning to solve. That is going to be the task at hand. And then there's supposed to be a performance measure. The reason why this is important is without measuring how well your model, your machine learning model is doing, how will you know if the problem you're trying to solve has been solved in the first place? So you need to have a performance measure. Usually one common performance measure that is used is accuracy. So over here, people usually use accuracy. So the way you measure accuracy is you can give your model, let's say, 10 inputs whose output you know. And if the model is able to predict correctly the output for 8 of them out of 10, then you know that your model's performance is 80% or 0.8. So one common performance measure is accuracy. And the experience we are talking about here, I mentioned in an older video that the way a machine learns is that you pass your data set, your labeled data or your training data repeatedly through your model, and then it comes up with some output. Initially, it's going to start with producing random output, and then once we get our hands dirty to build these things, you understand why things are the way they are. Initially, your model is going to come up with random output, and then based on that random output, it is going to come up with the cost or the loss, which is how bad or how well, depending on how you see it, how bad it is performing as far as the given task is concerned. And using some mathematics, usually calculus, it is going to calculate the adjustment that it needs to make to its internal representation, which we call weight or parameters. So it's going to make some adjustments to these internal representations of the model, and then it will feed in the data again. So the lesson here is that after every successive passing of the data set through the model, you expect that its performance is going to improve with time. So that is all captured in Tom Mitchell's definition, which says that a computer program is set to learn from experience E with respect to some task T. So the E here is the repeated passing of the data through the model. This happens during the training phase, but there are some other machine learning systems that we call online learning, which are models that have already been built and then they are used in production. But even as they are used in production, they still adjust themselves to suit newer input that comes in. So that also goes into the experience over here. So the more the model is exposed to the training data, the better it is expected that it gets as far as the performance is concerned. So these are two definitions of machine learning, and the whole idea is you are using training data that is usually labeled to let a computer capture rules or capture patterns on its own. And that is the difference between machine learning and traditional software engineering. So thank you very much for watching, and I'll see you in the next video.